Okay, so I first wanted to just quickly remind people about some definitions about in first order logic. So first order formula is something like this. I think it's easier to give an example than to give the definition. So where you have some quantifiers, and those variables that appear in the quantifiers are the bound variables, and then there are the variables that are not bound by quantifiers are free variables. And so this, and then I'm thinking of this in the language of rings or fields. And so if you fix the field K, you can try to interpret this and see what it means. Except it doesn't yet have a truth value because I don't know what X is. And so the truth of this statement over a particular field will also depend on what the particular value of X is. And so, but once you fix the field and you fix the value of X, then you can ask whether it's true. And if for any given field, you can take the set of all such X for which it's true. And that's the notion of a definable set. Strictly speaking, sometimes, I guess definable, often you're allowed to also use constants from K, but because I'm not going to allow that. So these are sometimes what people call, I think this is zero definable. And the logicians in the audience should always correct me if I say something wrong, because I'm not a real logician. So, okay. I also want to talk about families of subsets, families of definable subsets. So the setting for this is this. If I have a picture like this where I have, unfortunately, this is an m plus n dimensions. And I have m dimensions going this way and n dimensions going this way. And so and then I have two definable sets. So the D is a definable subset of k to the m plus n. Yeah, maybe I should have said, I mean, this is an example where I just had one free variable, but you could also imagine having many free variables, and then you get a subset not of k, but a subset of k to something. Okay, and so here, if you have a definable set here and a definable set here, so definable set. So this is in k to the m, and then you have the natural projection map here, and you can and I'm going to assume that it restricts to a map here. I'm not. B doesn't necessarily have to be the image of the projection, but it should at least contain the image. So okay, so then you have this just projection of definable sets, and so then you can for every point of B, you could take the fiber above it. You can take the inverse image, and then that'll be some collection of subsets indexed by B. And so any set so that's what I will mean by a definable family of definable sets. So definable family of definable subsets. Yeah, and again, I'm not going to allow constants in any of my definitions. So I guess strictly speaking, maybe I should say zero definable, zero, but I'll forget the zero. Okay. Yeah. Okay. So that was these are just things I'm going to need to use later. But the main subject of the talk are going to be finally generating fields. And so by finally generated, what does this mean? There are a couple of different ways you could say it. First, it should be a field it's a field that's finally generated, but finally generated over what? So, well, I mean in the absolute sense. So over its minimal subfield. So the minimal subfield is going to be, depending on the characteristic, it'll be either Q or FP for some P. And yeah. Okay, so yeah, so it's a field that's generated by finding many elements over that. Another way you could say it is you could use the theory of transcendent spaces to say, well, you start with, okay, let's first suppose it's characteristic 0. So you start with Q. It might be an algebraic extension of Q, but if it's not, then you can find some transcendental element, say T1. And then if it might be then algebraic over Q adjoint T1. But if not, then you can find another element that's algebraic, that's transcendental over what you have so far. And you can keep going like this, and well, eventually it'll stop. And then what's left will be an algebraic extension of this. And it's also finally generated, so if it's algebraic and finally generated, it'll be a finite extension of this. So, okay, so it'll be a field extension that's finite over over such thing, or else, or over, it'll be, or of, if it's characteristic P, same thing, that's Fp instead of Q. All right, so you could also think about it as being the function field of a variety of and in fact you can think of it as being a field of a geometrically integral variety over some constant field. And the constant field will be the relative algebraic closure of Fp or Q inside the whole field. So yeah, so over a number of, so which will be a number field or finite field. And that constant field we'll call K. Yeah, so this is it's a constant field. Okay, and finally, I could think of it as being I could let R be the ring or Z algebra that's generated by the generators, and then the field will be the fraction field of that. And so so R is going to be is a domain, is an integral domain that's finally generated as the Z algebra. Okay, so these are all equivalent ways of saying what a finally generated field is. Maybe I'll just draw some of these things as a picture. So let me just do the characteristic zero case. So that I start with Q, and then I could join all these indeterminates, form this purely transcendental extension. That's it's the field of rational functions. And then the big field would be a finite extension of that. So it'll be some K up here. And or I could also think about the largest algebraic extension of Q inside there, which will be some finite extension. In this case, it'll be a number field. And then it'll be containing this. It's not necessarily true these things generated, but these things are fine. This will be some finite extension here. And yeah, so this is finite. This is purely transcendental. Yeah, so this is so the T1 through Tn is the transcendence basis. Yeah, and this is a finite extension here. And okay, so yeah, and so in this case, this is the K is a number field, and that's the function field. Okay, any questions about this? Yeah.
2 questions, I think.
Yeah.
The first one, so what does geometrically integral variety?
Oh yeah, so I didn't say about that. So variety for me is so these are notions from algebraic geometry. So integral is the same as saying that it's an irreducible variety. It's not a union of two closed subsets, and it's also reduced in the functions on it. There's no nilpotence in the ring of functions on it. And geometrically, integral means that it stays that way even after doing a base change, even after doing a field extension. So because you can have a variety like defined by x squared minus 2y squared equals 0, that's irreducible over Q, but when you look it over a larger field extension, it decomposes into 2 lines. And so, yeah, so it's, okay, so, I wouldn't worry too much about it. It's just saying that it's not, yeah, okay, so that is what I said. But, yeah. So, just think about a variety. Probably when you think of a variety, you're thinking of a geometrically integral variety anyway. So, yeah, I could write out more maybe afterwards, but yeah.
But I have a second question.
Yes. Okay.
You said the constant field k in that case, in that definition, would be, say you start with a finite extension of q Tn. You said this was?
Maybe I'll write down the explicit definition of k. So in terms of, so k is the set of alpha in the capital K such that, okay, so then let me do the characteristic 0 case. So it's such that alpha is algebraic over Q, which means that it satisfies some polynomial equation with rational coefficients. It's a root of some polynomial. So, and you can check that you can prove that these things form a subfield of K, and in this case where capital K is finitely generated, this will be a finite extension of finite degree over Q. Okay, which is the same as saying it's a number field in this case. Yeah, and it'll be the same thing would happen if you replace Q, if you're in characteristic P, you just replace Q by FP. It's all the same. All right, any questions about that? Any more questions? All right, so let's see. All right. I'm okay. What? Oh wait, that's not what I wanted. Well, it's more or less okay. I just want to fix that back. All right. Well, okay. Wait. What am I supposed to? Oh, this is only. Okay, sorry. Okay. All right. I guess it's only when I'm at the bottom of the board that you want to fix. Sorry about that. Okay. So, all right. So. In terms of this description, I can define the Kronecker dimension of the finitely generated field. So this only makes sense for finitely generated fields. And so this Kronecker dimension, it's the same as the curl dimension of the ring R, which is defined in terms of the chains of prime ideals in commutative algebra. Or you can define it in terms of this, in terms of the transcendence degree. So the transcendence degree is the number of algebraically independent elements. So in the second bullet item there, it's the number n. So it's either this. In the case of characteristic P, you take this transcendence degree. But in characteristic, if it's characteristic 0. Then you take the transcendence degree over Q, you take the n, but you add 1. If characteristic 0. And the reason for doing that is, well, if you think about, suppose that K is just Q itself. So then Q is the fraction field of Z. But the dimension of Z as a ring is 1. Because you have a chain of prime ideals. You have the 0 ideal and then you have a prime. P times, yeah. So that's why you add 1 in this case. Okay, so all right. So let me now state the main questions about finitely generated field about the first order theory. So the first question is, so this is a question that. Well, it was implicit in some work by Sabag in the 1980s, and it was asked explicitly by Florian Popp in 2002. And so the question is, does the first order theory determine the field? So so given non-isomorphic fields, so non-isomorphic finitely generated fields, K and L, and can you find a first order sentence? So I'll just say sentence that is true when it's true for K, and false for L. So really it's a sentence that distinguishes those two fields. So another way to say this question would be for finely generated fields K and L. If you know that they're elementary equivalent, so the theories are the same, does that mean that they're isomorphic? I mean, this would definitely not be true if K and L were not finely generated, because, for example, if you take any infinite field K, as it was explained, in the talks yesterday, you can take an ultra power of that field and get a field of larger cardinality that has exactly the same theory. That's elementary equivalent to K. So, but there's hope that if we're restricting to this very small class of fields, that maybe it's true. Okay, so that's the first question. The next question, I'm going to give you 3 questions. Each one is sort of stronger version of this. This is one I asked in a paper in 2007. So given one field, one finely generated field K, can you simultaneously distinguish it from all the other ones with just one sentence? So is there a sentence that's true? It's true for K and false for every finely generated field. For every finely generated field, well, of course, other than K. So it's like the sentence that picks out K. And the third version of this. So this would be a sentence that picks out the singleton field consisting of the field K. But you could ask if you could find a sentence that picks out a whole collection of fields, a prescribed collection of fields. For example, maybe can you find a first order sentence that picks out all the number fields among the finely generated fields? Or maybe it picks out all the purely transcendental extensions of F7. Can you do that? And so, well, I mean, you're not going to be able to get any subset of the collection of finely generated fields because there are only countably many sentences, and there are uncountably many subsets of the collection of finely generated fields. But you could ask for is every reasonable class of infinite finely generated fields cut out by a single sentence. Okay, maybe I could tell you. In a discussion I had with Khrushchevsky, we came up with a reasonable definition of reasonable. And so I could tell you precisely what we decided this should mean, but maybe for the sake of time, maybe I'll skip that for now. Okay, but anyway, so there is a precise conjecture or question along these lines. Okay, so I want to tell you what's known about these questions and what's. So let me first talk about the case of global fields. So by global field, well, actually the simplest way to say this, given what I've already told you, is that these are finely generated fields where the Kronecker dimension is 1. And so that there are 2 kinds depending on the characteristic. It either means it's either transcendence degree 0 over Q, or transcendence degree 1 over Fp. So that means it's either a number field, in other words, a finite extension of Q, or it's a field of transcendence degree 1. In other words, it's the function field of a curve over a finite field. And those are called global function fields. So over some finite field. Yeah, okay, so for these, So Rumley, in a paper 1980, he proved, so building on earlier work of Julia Robinson and Ershoff, he proved that, well, first he proved that in such a field, you could give a uniform definition. Uniform meaning it doesn't depend on which field you're talking about. You could give a uniform definition of the family of all the valuation subrings of valuation subrings. So, for example, in a number field, this means for every prime, like for example in Q, it means you can get so for each prime you get the z localized at P, which is the discrete valuation ring associated to the prime P, and you can take the family of those, and I'm saying that'll be one of these. It'll be a definable family of definable subsets of Q. And not only do you do that, but you can find a single formula that does this simultaneously for every field, for every one of these global fields. And once you have that, you can use that to show that other sets are definable. And so as a sample corollary of this, you can say, for example, you can detect the characteristic. For example, because you can, if you have a global field K, you can, how do you figure out whether the characteristic is 0 or not? Well, if you have this definable family of valuation subrings, you can take the intersection of all those valuation rings. And yeah, so the intersection of all the valuation rings in K. And well, what will this be? I mean, if you do this for something like Q, then if you intersect Z localized at P for all primes P, it means you're taking a rational number such that no prime is allowed to appear in the denominator. And those are just that'll be the integers. And in general, in a number field, this will be the ring of integers of the number field. So, but if you do this over a global function field, then this intersection is like the rational functions that have no poles on a projective curve. And those will be just the constant functions. So you'll just get the little k. So in one case you get a ring like Z, in the other case you get a field. So you can detect whether something's a field, because the property of a set being a field you can write in first order terms. And so you just have to ask the question, is this intersection a field or not? And that'll detect the characteristic. By the way, this might be very strange if you're not, I mean, this is very special that we're restricting to these kind of fields. Because, I mean, we know that if you look at all fields, there's no way you can detect the characteristic in a first order way. As was said yesterday, if you have any sentence that's true, first order sentence that's true for the complex numbers, say, it will automatically be true for FP bar for all but finally many primes P. And so, yeah, so this is kind of a weird thing here. Yeah. All right, good. So, and also, well, once you have this valuation, this family of valuation rings, building on that, you can define the ring. Yeah.
How do you quantify with valuation rings in a first order way?
So all I mean by this is that I can find a definable family of definable subsets here, such that the fibers that appear, all the fibers, all the non-empty fibers, so all the fibers are the valuation rings, maybe appearing more than once. Yeah. And over some definable base. So if you take so I can find a D and a B such that for any point in B, the pre-image is a valuation ring. And also, as I vary the point little b over B, I get all the valuation rings. That's all I mean by this. Yeah.
So if you take a countable intersection, that's still first order or second?
Well, to get the intersection, I use a universal quantifier to say that for all points, once I have this thing, I can take a uniform. It doesn't even matter whether B is countable or not, although it is. But you can just take the set of elements that are for which such that for every point B, there exists a D. Yeah. There exists, the point is, yeah, do you see what I mean? You can, yeah, you can write down some formula that takes that. Yeah, okay, any other questions? Okay, so, all right, and so the last thing I want to say here is that you get a positive answer. So you can, it turns out you can, at least in the number field case, you can actually show that Z is definable, and in the function field case, you can get some kind of copy of Z. For example, you could take if you have this one transcendental element, and you can talk about its integral, its natural number powers. And you can get things like that. So you can get, and once you have Z, then you can use the fact that, I mean, anything, you can get all the sets that are definable in Z. So you can get all the, and you get so much power from that you can actually answer all three of these questions. So you get a positive answer to all three, Q1, Q2, and Q3. Okay, well, so restricted to global field. Okay, so now I want to talk about what you can say going beyond global field. Okay, anybody want to ask some more questions? Otherwise it's going to be really boring because you're just going to be watching me erase the board. Or maybe this is the most exciting part of the lecture. I don't know. Will I get every spot? I don't know.
So why did you answer Q3? That's the third.
How do you get Q3?
Yes, because I don't know what is reasonable yet.
Well, that's because I didn't tell you what reasonable meant. Yeah. So.
So it's
But every global field is reasonable.
Well, the notion of reasonable is a notion about subsets of the class of global fields. So you could take all the global fields of characteristic 3. That's an easy one. Or you could take all the global fields that are. You get the collection of all the FP adjoint T, where P is prime. Or you could take all the global function fields whose constant field is F4. Anyway, there are all kinds of things, any subset like that. I'm saying there's some first order sentence that's going to be true exactly for that subset. That's what it's saying. Yeah, but I mean, you have to do. I mean, there's quite a lot of work to actually prove. Yeah, and I'm not even sure if I can't even remember. I don't think Rumley maybe said Q3 explicitly, but it follows pretty easily from what he did, that you can do this. I mean, what he really proved is that there's a uniform by interpretation of Z, of the integers, in this field. So you can define something that has the same character as Z using in the arithmetic of K, and then vice versa. You can model the arithmetic of K in terms of Z, and then there's, okay, this, you can go back, I mean, it's interpretable, anyway, I don't want to give the full definition. But. All right, so any other questions? All right, so to do things for more complicated finely determined fields, it's going to be useful to use some things about quadratic forms, and in particular, the quadratic forms that are very nice are these things called Pfister forms. So this is just a notation for a quadratic form. This one means this quadratic, so just think of A as being some number in your ground field, and you write down this quadratic form in two variables. And if I write A comma B, this means this is going to be a quadratic form in 4 variables, and the coefficients are the products of all subsets of A other than B. So you have 1 AB and AB. Okay, so and then the next one to have 8 would be 8 variables and so on. Okay, so you have this. These are called Pfister forms, and they have their arithmetic is quite nice. And Florian Popp used what was known about these Pfister forms to prove that you could detect the Kronecker dimension in a first order way. So, well, you fix a non-negative integer m, and then I want to say, how do you detect whether the Kronecker dimension equals m? And I can tell you there's going to be a first order formula here, and the first order formula is this. So, okay, I'm not going to write it out explicitly as a first order formula, but what I write will be easily convertible. Okay, so the first case is, it could be that characteristic is 2, that's what this is saying. And if the characteristic is 2, then it's very easy to detect the Kronecker dimension, which is the same as detecting the transcendence degree. Because if you have a field K of transcendence degree m, and you look at the field degree of K over the subfield of squares, in other words, the image of Frobenius, then that will be equal to 2 to the m. Yeah, because for example, if K were just the field, let me just do an example. So if K is the field F2 adjoin m variables, so that's an example of a field of Kronecker dimension m, then if you take the squares of all these elements, you'll get just another rational function field where the variables that's generated by the squares of these things. And then this field, as an extension of that field, is an extension of degree 2 to the m, because you have to adjoin m square roots to get from here up to there. And so, yeah, and it's the same if you take a finite extension of that, this degree stays the same. Yeah. In fact, I think I forgot, I think the name for this, Urchoff invariant or something?
Or experimental simplification, or...
Okay, I've heard something...
Invariant is one name.
Okay, anyway, I guess, okay, whatever. But that's only for characteristic 2. You could do something similar in characteristic 3, but I want to do something that works for all characteristics. And in fact, there's going to be something that works for all characteristics not equal to. So okay, so it's going to be this, or the characteristic is not 2, and in this case I'm going to use quadratic form. So the claim is that then you impose the condition that every Pfister form where you have m plus 2 of these should represent 0, except maybe over the field where you have a square root of -1. So that represents 0. So represents 0 just means that the quadratic form, that when you set this equal to 0, there's some solution other than just 0, 0, 0, 0, 0. Okay, so yeah, so for example, in the number, if you're in the number field case, for example, if you take a quadratic form of 4 variables, a Pfister form with 2 of these things, it doesn't necessarily represent 0. But if you take 8, then if you have a quadratic form in 8 variables, well, over Q, it still might not have 0 because it could be the sum of squares of 8 variables, and that's not going to represent 0 just because of the real obstruction. But over a totally imaginary number field, any quadratic form of rank 8 will have 0, and particularly these, yeah. Okay, so this is the full statement then.
Sorry, you need n to be minimum of the property, shouldn't you?
Oh yeah, sorry. I guess sorry. This should be. You're right. So I guess. Yeah. So you're right. I need to say that it's. Okay, let me just do it this way. So let's change this to this. You're right. So, yeah. Is that good? Okay, good. Yeah, sorry about that. Okay, so yeah. Yeah, and then once you have this, you can also get exactly equal to m, because you say it's less than or equal to m, but it's not less than or equal to n minus 1. Yeah, okay. Okay, good. Yeah, so this answers, yeah, so okay, so this is a partial result towards these questions, but it's not enough to identify, this doesn't quite distinguish two fields, it only distinguishes fields that have different Chronicle dimension. Okay, so then I wrote a paper where I proved a couple of things. First, that there exists a first order sentence phi such that it holds true for a finely generated field. So yeah, so this K, I'm always talking about finely generated field. So this is generated field. It holds if and only if the characteristic is 0. So you can't actually detect the characteristic once you restrict the finely generated fields. I also proved that there exists a first order formula. So whatever that Greek letter is, X. That in any finely generated field K, it holds for exactly when X is in the constant field. So it detects, it defines the field little k. And then the third part is you can detect. There exists another first order formula. This time, for each n. Let me say for each n. So for given n, there exists a formula phi sub n in n variables that in any finely generated field k, it detects whether the numbers you plug in will be true exactly when these numbers in the field are algebraically dependent over the constant field. Yeah. So it's detecting algebraic dependence.
What's little k?
Little k is the constant field of little k. I'm always denoting by little k the constant field of capital K. So little k is always a finite extension of fp or a finite extension of q. It's the largest finite extension that's contained in the big finite in the capital K. And so that's what that's the constant.
How complicated are the formulas?
How complicated? Well, they're quite complicated, but it fits in an article in a math that was published. Okay.
Did you figure out the complexity?
The quantifiers, how many?
How many quantifiers? I don't remember. It's not ridiculous. As nobody ever has formulas that have nobody ever writes down a formula that has 100 alternations of quantifiers, as Ted was saying. But it's something. I don't know. I guess if you want to, you can make a project to try to get a simpler one and try to see what's the smallest number of alternations of quantifiers you need to find these. But or maybe I can say one more thing about these. Okay, so that's what I did. So one small note is that actually, if you know P2, it's very easy to get P1 because, well, if you know how to define the constant field, well, then you want to decide what the characteristic is. The characteristic of K is going to be the same as the characteristic of the constant field. And so then the question is, how can you, I mean, and a constant field is either a finite field or a number field. So now all you have to do is, how do you just tell the difference between a finite field and a number field? And well, one way to say it is that, well, you can use Pop's result, because finite field and a number field have different Kronecker dimensions. Or the number field has Kronecker dimension 1. So from Pop's result, you can get, if you get P2, you get P1 for free. Okay. So continuing the history, so recently, Philip Dittmann and Bjorn Poonen, they proved in a paper 2023. So building on all this stuff above, building on the above, on both Pop's result and these results, and also some work of and on work of Thomas Scanlon. So they got a full positive answer to both Q1 and Q2. So then they're able to identify any single finely generated field, distinguish it from all others with a single first order sentence. So I guess there's a small caveat here, which I'll write in some almost invisible color. So this is conditional. In the case of characteristic 2, it's conditional on knowing resolution of singularities for algebraic varieties. So that's the statement. Yeah. So if the characteristic is 2, so this is saying that every variety is birational to every is a smooth projective variety over that field.
So what do you mean by
regular? Let's say. Yeah.
What do you mean by case? So it's definitely known that for every field of characteristic not 2 finitely generated, there is a formula, and for
there's a formula that works.
To know that the formula works in characteristic 2, you need this condition.
I can't. It might be that the formula depends on. I can't remember. Maybe you need to use the resolution to write down the formula. Because it's one formula for each k. Do you?
Yeah, I don't think you need. I mean, it's just that the formula works. Depends on. I mean, right? You can.
Is the formula? You don't need to know the resolution. Well, I mean, anyway, if the resolution exists, you can find it, I guess. But I guess, it's not uniform, is it? Or
no.
It's not. So anyway, so it's just a question. So yeah. So I guess.
If you can immediately distinguish between characteristic 2 and not 2 by just asking whether 0 equals 2 or not.
Yeah, that's not much.
Definitely know that in characteristic not 2.
Yeah, so for characteristic not 2, there's no condition at all. There's just no.
So can you say what's special about characteristic 2?
I guess the proof relies. I guess it uses things about quadratic forms and things. So it gets annoying in characteristic 2. I don't know. Maybe there's some way. Maybe that could be another project for this semester to try to do this unconditionally, even in characteristic 2. But maybe I don't know how feasible that would be. Yeah.
So is it fair to say that for characteristic 2, it's dependent on a conjecture? Or?
Yeah, it's dependent on a conjecture that I think most people believe. So I think people believe. That resolution singularity is holds, and so So I think. Yeah, so I think it's anyway. So I think So it should be. So all this should be true. So the answer to question 2 should be yes. So you should be able to identify to single out any finely generated field you want, distinguish it from all others with a single sentence, depending on the field you're trying to use to the existence. Yeah. All right. Any more questions?
Does their work shed any light on question 3?
Well, I guess it sheds a little bit of light. I don't know. I think maybe it remains to be. I mean, it's definitely good. I mean, it's definitely going to be useful if you're hoping to do question 3. I think. But I don't know. I mean, we might be pretty far from getting question 3 still. I don't know. All right. So in the remaining time, I'm going to try to show you how. Well, I'm going to show you what the parts that I know best, which is some of proving P2. And I'll just to save time, I'll do this only in the case of where the characteristic is 0. And also I'll assume that. Just to simplify things, I'll assume that there is a square root of -1 in the field, so I just don't have to join it all the time. Okay, so I'm probably not going to have time to do all this, but let me get started. So, all right, so I mean, the whole proof, yeah, so it's a 7-step proof. Okay, so here's step 1 is that there's an elliptic curve. Yeah, so I'm fixing this field, the finely generated field, capital K. And so I want to say there's an elliptic curve over Q such that the group of rational points, which in general is known by the Mordell's theorem, it's known to be a finely generated abelian group. And all I want here is that it be not a finite group. I mean, sometimes it's finite, but I want it to be infinite. But I also want it to be true that when you look at the points on the elliptic curve, the solutions to the equation that with entries in the big field, you get nothing more. You get nothing more than already existed over the constant field. Okay, so how do you do this? So how do you construct such a thing? So first, let me choose a K variety. I'll represent my function field as the function field of a variety V. So whose function field is K. Okay, and then we'll choose an elliptic curve of positive rank. So meaning with infinitely many rational points, and such that its base change to K is not a quotient of the Albanese variety of V. So so I'm using some algebraic geometry here. So it turns out that there's an abelian variety of higher dimension that V maps to, and such that all maps from V to an abelian variety factor through that one. It's sort of a universal abelian variety to which it maps. In particular, if V maps to any elliptic curve, the map has to go through here. And so by choosing an elliptic curve that's not a quotient of this, you're getting an elliptic curve for which there are no maps from V to E at all, except for the ones that are constant. They're just sending the whole variety to a point. And so once you have that, then you'll get that such an E will work. Oh, maybe I should say, why can you do this? Well, an abelian variety there are only finely many isogeny types of elliptic curves that can appear as quotients. And each isogeny class over a number field has only finely many elliptic curves in it. And so this condition is really only excluding finely many isomorphism types. But on the other hand, there are infinitely many isomorphism types of elliptic curves of positive rank. So there are lots of choices for the E. So yeah. So this condition excludes only finely many. so many E. So there are plenty of choice. So it's easy to arrange that. Okay, and then yeah, and then E of k. Another way, when you take an elliptic curve over a field and then you look at its points over a function field, that's the same as looking at maps from spec k to E. And spec k is the generic point of V. And so this ends up being the same, so tautologically, it's the same as taking rational maps from V to the elliptic curve over the constant field. And on the other hand, if you look at the points of E over little k, under this interpretation, though that corresponds to the constant maps among these rational maps, the constant maps from V to E of k. But we chose this condition is exactly what guarantees that all the maps from V E are that you only have the constant ones. So you get that this is the same, and so that gives you this condition. Okay,
So what's the use of square root of minus?
Oh, I haven't used that yet,
Yeah,
so that's coming.
Okay.
Yeah. I mean that's to use things about quadratic forms. So
Yeah.
Okay. So step 2 is that for each prime p. So now I have this elliptic curve, and I want to say that for each prime p, if I look at this set of rational points, then this is p-adically dense. In some neighborhood of 0 in the set of p-adic points on E. Okay, so yeah, and the proof of this is simply that there exists, yeah. I mean, if you look at the structure of this thing, you can think of this as a p-adic Lie group, a one-dimensional p-adic Lie group. And it's true that for any p-adic Lie group like this, if you look at a neighborhood of there's going to be some neighborhood of the origin that looks like a neighborhood of QP itself. In particular, you can find a subgroup in here that's isomorphic to a copy of the group ZP. And so you have so it's an open subgroup in here, but this is also a compact group since E is projective, and therefore this open subgroup has to have finite index. So there's a copy of. So in other words, this group is almost just a copy of ZP. Up to finite index, it's just a copy of ZP. And it makes it easy to understand the topological group, the properties of it. And in particular, all I need to know, I mean, I know this is an infinite group. So you have an infinite group here, it's going to intersect this in something infinite. And what does an infinite subgroup of this look like? Well, I mean, any infinite subgroup, all I need to know is that an infinite subgroup of ZP is dense in some neighborhood of 0. In fact, the closure will be equal to p to the k times ZP for some k. So in some neighborhood of 0. So that finishes the proof of step 2. Okay, so I don't know how much time I'm going to have. Okay, but how many? There's going to be okay, so now I want to prove that there exists a subset of the constant field such that, first of all, I want it to be definable in the first order arithmetic of the big field. But also, I want it to be true that when I look at it, the rational numbers that are in there, then this should be p-adically dense in QP, not just an open subset, but in QP itself for every p. Yeah, I want this to be true simultaneously for every prime p. So how do you make this? So the proof of step 3 is you choose a uniformizing parameter. You choose in other words, you choose a a local coordinate on the elliptic curve. So z at the origin on E and E. So the picture is this: you have this curve, and you have this p-identity group of points, and somewhere over here is the identity of the group. And now I'm going to choose a coordinate, just a coordinate that increases along here, and so which I can think of as a rational map to. And then here I just have the QP itself, and now I know that the rational points, which is some countable subset of it, by assumption I arranged it. I know that the rational points are p-adically dense around 0. So there's the closure of the rational points contains a little open neighborhood of 0. And if I look at its image under Z, I'm going to get in QP. I'll get a countable collection inside this field QP that contains at least an open subset of that. That's not enough because I want it to be p-adically dense in the whole thing. So how do I do? So yeah, so the strategy, I'll first let T be the set of Z coordinates of all the points on E. That's a definable set because it's just a set of points satisfying some equation, and then I look at its image under some ratio of polynomials. And so this thing, at least it contains a bunch of rational numbers here that are dense in this neighborhood. And now I'll take S to be the set of ratios of T1 over T2, such that T1 and T2 are in T. And the point is, if you know that you can approximate any points in this neighborhood, then any number in QP will be a ratio of 2 points in that neighborhood. And then you can approximate those numerator and denominator. So this will be something that's dense in QP then. Yeah, and this description didn't depend on P, so it works for all P simultaneously. All right, good. So, all right. So now for the hard step. Yeah. Okay. Any questions about this?
Can I ask a question about that? Why is it that all the rational maps are also constant?
Because the well, okay. So I guess there's a theorem that all the rational maps. Let's see. Yeah. So I mean, the Algebraic also classifies all rational maps to it. In fact, all the rational maps I think it's right that all the rational maps from a smooth projective variety to an abelian variety, they're actually all defined everywhere. So there's some geometry, it's actually no different when we talk about rational maps or morphisms. Okay, so any other questions?
So what is a uniformizer at x0?
What does uniformizer mean? Is that the question?
In this elliptic curve.
Uniformizer just means it's a function. So if you're thinking of it as an element, it's an element of the function field of the elliptic curve. So it's a rational function defined on the elliptic curve that vanishes to order 1 at the origin. So it doesn't have a double zero, for example. Yeah. So it's like, and so if you have such a function that vanishes to order 1, it's like an analytic coordinate. So the map Z is sort of analytically an isomorphism, at least in the neighborhood of the origin. Yeah. So that's.
And works for all P.
Yeah. The uniformizer is. Yeah. It's defined independently of P. So you define it over, you can have it define it over Q. So I mean, I could be very explicit, in fact, about that. If you take an elliptic curve in the usual form, where it's like y squared equals x cubed plus ax plus b, the function capital X has a double order pole. It has valuation -2 at the point infinity, and the y coordinate has valuation -3. So if you take x divided by y, that's a rational function that vanishes to order 1. at the origin. And you can use that as your z if you want. Okay, so yeah. Oh, sorry, I'm out of time. But maybe I'll just write this step here, and then I won't have So if you want to, so if you have an element of capital K, so remember what we're trying to do. We're trying to characterize the constant field inside by we're trying to show that the constant field is definable by a first order formula. And so I'm going to tell you what the formula is. And so and so you have to. So it's using this definable set S. So you define it this way. You take the Pfister form S1, S2, T minus S3 over K, and you ask that this one represents 0. Okay, so this is the main step. So I'm out of time. So all I'll say here.
You can take extra time, it's just lunch break.
What do you say?
Extra time, it's just lunch break.
But I like lunch. Okay. Anyway, I'll just say briefly what happens here. So suppose T is in the constant field, okay, which is some number field. So then, I mean, S is also contained in the constant field. So so that means that all these S1, S2, and S3, everything here is in the constant field. And so you have these three numbers in a number field. And so you have a Pfister form with 8 variables over a number field. And the number field contains square root of -1 by assumption. But if you have a quadratic form in 8 variables, I mean, actually, even if it just had 5 variables, it automatically will have a non-trivial 0. That's some real number theory. And so this thing, if T in addition to these things are all in the number field, then this will automatically have this quadratic form will automatically have a non-trivial 0. And the trickier part is to show that if T is not in the number field, so that means it's really like a non-constant rational function on the variety. Then you can choose these S1, S2, and S3 in a clever way to make sure that this thing does not represent the field. You essentially want to make these S2 and S3 sort of be like independent local coordinates on the spec R. And then okay. So it's I don't have time to do that. By the way, this is not quite enough because this shows that you can define little k inside this one field k. But if you look carefully, my definition of this is a first order definition, but it depends on the capital K. And I was claiming that you could do it uniformly with a single formula that didn't even depend on which finite general field you're talking about. And so what you would actually do is you have this thing that depended on the choice of elliptic curve, but then to do the rest of the problem, you take all elliptic curves, and you define all the subsets this way. You get a big collection of sets, and then among those sets, the little k appears in them. And then you select from that set all of the fields in that family of subsets. And then you take only the fields that are of the correct Kronecker dimension. And so then all those fields are contained, then you have a collection of fields that's contained in K. A definable collection. And then you take the union of that. And that union will all be inside K, but one of those sets is actually K itself. So the union will equal K. And so that's how you define it in a uniform way. All right, that was steps 5 through 7. So